Welcome to the course Business Analytics and Data Mining Modeling using R part 2. So, in previous lecture we started our discussion on cluster analysis. So, let us do a small review of what we discussed so far. So, we talked about cluster analysis and the usefulness of this particular technique, the applications, the scenario. We also talked about the main idea. We discussed that to characterize the clusters in ways that could be useful for the for generating some insights. So, that being the main idea. So, then we also discussed this particular data set, breakfast cereals, and we did a small exercise in R Studio as well. Then we talked about two types of clustering algorithm, hierarchical methods and non-hierarchical methods. We understood when these methods could be useful. Then within hierarchical methods we talked about agglomerative methods and divisive methods. We also touched upon non-hierarchical methods, and through an exercise in R Studio we understood the main how these methods, cluster analysis methods, are typically implemented. We understood that distances between observations, so those become the major part of all cluster analysis algorithms. So, we also started our discussion on the types of distances that we need to compute in cluster analysis. Distances between two observations being the first one, and the distance between two clusters being the another one. So, let us start from this point. So, we talked about how distance metrics can be also be conceptualized or thought of as the dissimilarity measures. So, many of the popular similarity measures can be used because they can easily be converted into dissimilarity measures, and therefore can be used as distance metrics. So, the kind of metrics that we are going to use as distance to measure distance for our cluster analysis would be either directly based on distance kind of formulas, or would be based on similarity formulas. So, we started our discussion with this two observation. We can think about two observation. First one, observation I having coordinates as xi1, xi2 up to xip. Then observation j having coordinates xj1, xj2 up to xjp, where p is the number of variables to be measured. So, p is akin to what we used to have in our supervised learning techniques, the number of predictors. So, the p essentially is the same. However, we do not have any dependent variable as such in unsupervised learning methods. So, we use this notation dij to indicate the distance between two observations. We also talked about some common properties that has to be satisfied for a metric to be defined as to be accepted as distance metric. So, these properties are non-negative, self proximity, symmetry, and triangle inequality. So, these properties, as we discussed in the previous lecture, have to be satisfied. Then these are some of the popular metrics: Euclidean distance metric, correlation based similarity, statistical distance, Manhattan distance, maximum coordinate distance. So, these are some of the metrics that we are going to cover in today's this particular lecture. We also will also start our discussion on few metrics about categorical data. So, let us start with the Euclidean distance. So, we were able to discuss to some extent this particular metric in previous lecture as well. So, Euclidean distance, as we know, this is the formula, this being the most popular distance metric formula, as we can see in the slide. This is as we talked about, this is very scale dependent formula. So, any particular variable which is having or carrying larger scale will obviously dominate the distance computation, will obviously dominate the distance value. Therefore, we need to overcome this particular issue. So, one solution is to normalize or standardize the standardize all continuous variables. right. So when we talk about standardized, essentially it is computing Z score, and which is nothing but subtracting the actual value by mean value and dividing by standard deviation. So in that fashion we can bring all the numerical variables into similar kind of a scale. We did a small exercise in our studio for this as well. So let us discuss some other metrics. So what are some other distance metrics for numerical data? So first, before we start with them, few more points. Selection of distance metric, why we need. So some people might think that we have Euclidean distance metric, why not use it all the time. So there are few reasons for this, why sometimes we might require to use some other metrics. So few points have been noted here. So selection of distance metric plays a major role in cluster analysis. Typically which particular metric is going to be suitable for which kind of problem, which kind of data set and situation, for that domain knowledge becomes important part. So depending on the domain knowledge, different distance metrics might be suitable for for clustering task as such. So variables being used in this analysis, their interrelationships, types of these variables, whether the variables are numerical in nature or categorical in nature, whether they are ordinal, nominal or numerical. So whether the outlier, whether there are any outliers in the data set. So all these things have to be kept in mind, have to be analyzed while deciding which particular distance metric to be used for clustering task. Clustering, we also have to think about sometimes whether the clustering is to be done using a small number of dominant variables or multiple variables are to be used. So this kind of scenario will also will also play a role in terms of what distance metric we would like to use. So let us move forward. So some of these scenarios that we talked about, some of the regions that we talked about, we will be able to understand them better after these few points. So these few points are related to Euclidean distance and how it might not be the preferred metric in some scenarios. So what are these scenarios? So when we want clusters to be created mainly using some dominant variables and limit the influence of other variables. So this one scenario where Euclidean distance metric might not be useful because we would have to do unequal weighing and instead of normalization. So for Euclidean distance metric to remove its scale dependency, we normalize. However, so that essentially brings kind of equal weighing kind of scenario in Euclidean distance metric. However, in some situations because we would like to account for some dominant variables a bit higher than some other other variables. So in that in those situations unequal weighing becomes important. So therefore Euclidean distance metric might not be the preferred distance metric because after normalization it would not be able to do that. The other scenario is when variables are strongly correlated. So as we know that as we this particular aspect we have discussed in our previous course as well. So Euclidean distance metric cannot account for correlation between variables. So there is another metric called statistical distance metric or Mahalanobis distance, which we have discussed in the previous course as well. So this metric is a better choice in comparison to Euclidean distance metric because it can account for the correlations between variables. So we will see how this particular metric is going to be useful in such situations. Another scenario where Euclidean distance metric might not be preferred is when outliers are present and removal of these points is not desired. So, as we can understand that Euclidean distance metric, if the outliers are present, then they can significantly influence the distance computations. And if we for some regions, because those points might be very important for the analysis as such, analysis as a whole. So, therefore, we might not be interested in deleting or removing those points. So, therefore, Euclidean distance metric in such a situation might not be a preferred choice. So, we can use because we can use some other distance metric which are robust to these kind of situations, outlier, presence of outliers. So, Manhattan distance is one which could be used. So, what is Manhattan distance? We will discuss that in this particular lecture itself. So, we talked about these few situations. One being when we are trying to account for dominant variables, we are looking to give them more weightage, and another situation being when we are looking to incorporate the high correlation between variables, and the another situation being the presence of outliers. So, these are some of the situations where Euclidean distance metric might not remain the preferred choice. So, now let us start our discussion of these some other metrics which could be useful in different scenarios. So, let us start our discussion with the this metric, correlation based similarity. So, we all understand the correlation coefficient. So, this particular metric is actually based on that. So, distance metrics measure dissimilarity. So, we can also think about, as I have talked about while discussion of cluster analysis, that distance metrics, just like similarity measures can be used to can be converted to a measure dissimilarity, and therefore can be used as distance matrix. Similarly, distance matrix can also be used to measure dissimilarity. So, similarity measures can be converted to measure dissimilarity, and therefore can be treated as distance matrix. So, when we think about the correlation coefficient, right, the formula is in this particular slide, as you can see how correlation coefficient is computed. So, when we think about the correlation coefficient, it is essentially computing a similarity between two variables, and the square of this correlation coefficient can be used as a similarity metric, and this kind of formulation which we can see in the last point in the slide, Dij 1 minus Rij square. So, the square of this correlation coefficient, now this is being converted into a dissimilarity metric, and therefore can be used as a distance metric. So, if we look at this particular metric, so essentially we are trying to measure the similarity between variables, and that similarity is being converted into dissimilarity, and therefore being used as a distance metric. So, this is one metric that can be used to compute distances. The second one, the more important one of the more important metrics is this one, statistical distance. So, also called Mahalanobis distance. So, this particular metric can account for correlation between variables. In the sense, the contribution of highly correlated variables can be lowered in comparison to the variables which are uncorrelated or mildly correlated. So, this particular formula, as you can see in the slide, Dij is square root of this xi minus xij transpose, and the S inverse, where S is the covariance matrix for vectors xi and xj, and then under square root itself the multiplication by xi minus xj. So, you can see S inverse, this is the inverse matrix of S. So, this is nothing, in a sense we can think about S minus 1 as the p dimensional extension to division. This particular donation apostrophe donation denotes a transpose operation. So, this formula is the statistical, this is how we can compute the statistical distance, and as you can see, because the formula itself is accounting for because of the presence of covariance matrix, is in a way accounting for the correlation among variables, and as I talked about, contribution for highly correlated variable is lowered in comparison to the same of uncorrelated or mildly correlated variables. Then there are few more metrics which can be used. For example, Manhattan distance. So, Manhattan distance, this is also similar to city block distances that are used. So, this distance metric uses absolute differences instead of square differences between coordinates, as you can see in the formula itself. So, Dij is being defined as summation of m1 to p, and then absolute difference between xim and xjm. So, absolute of xim minus xjm. So, here instead of incorporating the square differences in other formulas that we have discussed so far, typically we are using square differences. In this case, the Manhattan distance, it is using the absolute differences between coordinates. If we go back, there was one important point where we said that Manhattan distance could be useful. Let us go back to the point and discuss that particular aspect. Presence of outliers. So, when outliers are present, we said that more robust distance matrix such as Manhattan distance could be used. So, now you can see why this was mentioned, because the other matrix, for example, Euclidean distance matrix itself, the squared differences between coordinates are there in the formula. However, if we look at the Manhattan distance, just the absolute difference between coordinates is taken there. So, if the outliers are present, the squared differences will actually lead to more variation and more influence being accounted, more influence of outliers being accounted. But if we use the Manhattan distance, because it is just using the absolute difference between coordinates, so the contribution of outliers is a bit lower. So, comparatively Manhattan distance is going to be more robust to presence of outliers, because their influence would be moderated. So, let us go back, and so there is one more metric that could be used to compute distances for numerical data. So, this is called maximum coordinate distance. So, this particular distance metric is again going to use the absolute difference, but this is just between the coordinates which are the farthest. So, if we look at the other distance metric, there more often than not we are using summation. So, the different coordinates, we are taking differences or absolute differences or square differences, and then we are summating all those values and using the final value as the distance final distance value between two observations. However, if we look at this particular metric, maximum coordinate distance, we are just identifying two particular coordinates which are farthest in comparison to other pairs of points, other pair of coordinates. So, if the same is reflected in the formula, you can see Dij equal to maximum of m1 to p, and then we are taking the absolute difference xim minus xjm. So, we are just looking to identify the coordinates which have the maximum deviation. So, though that this particular difference is being taken as the distance. So, that is why the name is also suggesting the same maximum coordinate distance. So, sometimes this particular distance metric can also be useful. So, we will see that while our discussion of cluster analysis in coming lectures as well. Now, all these metrics that we have discussed so far, they involve numerical data. So, typically all these metrics that we have discussed, maximum coordinate distance, Manhattan distance, statistical distance, correlation based similarity, and the Euclidean distance, all of these metrics, they are for numerical data. So, what if what if the categorical data is present? So, we would still like to perform the task of clustering even in the presence of categorical data. So, are there any metrics which could be used for distance computation? Because if you think about distance, typically it is concept that we naturally associate with numerical data. But distance, can this concept can be extended to categorical data? Can we do some sort of quantification and use that use the same for our cluster analysis to perform our task of clustering? So, yes, there are metrics which could be used for categorical data. So, we are going to discuss a few of them. So, if we look at the distance matrix for categorical data, they are mainly based on similarity measures, which makes sense also, because the distance computation as such is because that is typically applicable for numerical data as we talked about, and will not make sense for categorical data. So, essentially what we are looking for when we say distance matrix for categorical data, we are essentially trying to measure the similarity or dissimilarity. So, we can always talk about the similarity between two observations based on the attributes that they have for a particular categorical variable. So, two observations might have the same attribute for a categorical variable. For example, if we are talking about the status, where the particular record particular customer is whether the customer is a student or employed or retired. So, in that case, two observations, two of the customers might be having the same attribute. They both might be student, they both might be employed, or they both might be retired, or they might be different. One might be student, one might be employed, or the other one might be retired. So, we can always look at the similarity. So, if both are student, then we can take that as an evidence of similarity. If both are different, one is a student, the other one is employed, we can take that as evidence of dissimilarity, and now quantify this information and use this in a distance like as a distance value for our cluster analysis. So, the main idea is similar to this what I just discussed. So, mainly based on similarity measures. So, now extend this thought to our p dimension. So, suppose all p variables are dummies. So, right now we are only thinking about the categorical variables. The variables that we have in our final tabular format, right. So, as we have discussed in our previous course, that if the categorical variables are having more than two categories, we can always create dummy variables, and and then those dummy variables are then used for formal analysis, right. So, similarly we can think about all our p variables to be dummy variables, and they are having ones and zeros indicating presence or absence of a particular category or attribute. So, as you can see here, we have a small table here which has which we are going to use to understand this particular concept. So, we have record I and record j, and both these observations have we have p variables, and this particular table 0 and 1 and 0 and 1, as you can see, is indicating the number of variables. So, for example, record I 0 and record j 0. So, a is there. This a is actually indicating the number of attributes which are present, which are absent for both the observation I and j. 0 denoting the absence and 1 denoting the presence, and these numbers are actually denoting the number of those attributes which are present or absent. So, in this case, since 0 is denoting the absence for record I and record j, a number of attributes are absent for both these records. So, the same thing is mentioned here in this slide. A is the number of attributes which are absent for both the observations I and j. If we look at the another value here in this table d, So, D is the one indicating presence. So, D essentially is indicating the number of attributes which are present in both the records I and j, both the observations. So, this is what we have mentioned here. D is the number of attributes which are present for both the observations I and j. Now, there are going to be certain attributes which might be present for one and absent for the other one, right. So, you can see here C is the number of attributes which are present for record I, because it is against 1 in record I, but against 0 in record j. So, we can see that C denotes the number of attributes which are present for observation I, but absent for observation j. Similarly, B is the number of attributes which are present for observation j, but absent for observation I. So, these numbers tell us some story. So, if we look at this particular value D, so D indicating the number of attributes which are present in both the observation, thereby telling us giving us some sort of evidence of similarity. So, D is essentially standing for the similarity between two observations, these two observations, observation I and j. If we look at A, which is again indicating the absence of something. So, if we are okay with this idea that if something is absent between two observations, and taking it as a similarity between two observations, that this value A can also be accounted for. However, if we look at the B and C, so these two numbers definitely indicate the dissimilarity between these two observations I and j. So, if we look at this information, this particular information that we have just understood can be used to quantify the similarity and dissimilarity. So, let us look at the metrics that actually can do this for us. So, there are two metrics that we are going to talk about. One is the matching coefficient, another one is Jacob's coefficient. So, if we look at the matching coefficient, the value is the way we define it is A plus D divided by P, where P is the total number of attributes. So, it is the summation of A plus B plus C plus D. So, if we look at the we focus on the numerator part. So, in the numerator we have A plus D. So, A indicating the number of attributes which are absent for both the observations, and D indicating the number of attributes which are present for both the observation. So, both A and D presence of a number of attributes and absence of a number of attributes, we are taking that as a similarity, and we are using that in this numerator part of this particular coefficient, matching coefficient, and then dividing it by total number of attributes. So, this gives us a ratio which we are taking as a this proportion in a way indicating the similarity between these two observations. However, some people might argue that absence of something, if something is absent in both the observations, that would hardly indicate the similarity between two observations. Rather, it is adds some uncertainty between two observations in terms of similarity or dissimilarity. So, there is another coefficient which does not take the number of this value of A into account. So, Jacob's coefficient you can see in the numerator part and the denominator part, in both the parts the value of A has been taken off. So, A has been ignored because absence of particular attribute in both the observation is not being taken as a similarity or dissimilarity. It is being considered that we are uncertain about it, whether these attributes which are absent, whether they would have indicate some similarity or dissimilarity. So, A has been taken out of this formula. So, in the numerator we are just left with D. So, D indicating the number of attributes which are present in both the observations, and in the denominator we have just B plus C plus D, and therefore, we get a particular ratio, a particular ratio value which will indicate the similarity between two observations. So, the same point is mentioned here in this slide also, that Jacob's coefficient ignores absence of variables. So, you can see further that since presence of an attribute in both the observations can be taken as evidence of similarity. However, same cannot be said about absence of an attribute, since it brings uncertainty. So, therefore, the value A has been ignored. So, with this we will like to end this session here, and in the next session we will start our discussion of this distance matrix for both numerical and categorical data. So, we are more likely to encounter scenarios where in our data set both kind of variables, numerical and categoricals, both kind of variables are present. So, how do we go about doing our task of clustering? So, for that we need some similarity matrix or distance matrix which can incorporate, which can be used for both kind of data, numerical and categorical data. So, there is this one matrix, Gauber's matrix, similarity matrix. So, we will discuss about this one in the next lecture. Thank you.